Hi folks, the last part of this investigation is to try to figure out the meaning of a rational exponent. And since rational numbers can be expressed as fractions, that's the vehicle we're going to take to figure out what a rational exponent means. And for now, we're actually going to stick with a special type of rational number, so it's going to be 1 over some integer. Okay? I'm going to do this slightly differently here. So here's an example of a number that I'm trying to define. Okay, 3 to the exponent of 1/2. Okay, so again, I want to try to use the exponent laws here. So I want to create an exponent or a power that I can actually work with. So I know if I take 3 to the 1/2 and I multiply it by itself, okay, so 3 to the 1/2 times 3 to the 1/2, well, that satisfies the conditions for the product law of exponents. So I can just add the exponents and keep the base the same. So 3 to the 1/2 times 3 to the 1/2 must be equal to 3 to the exponent 1, or just 3. Okay? But we've seen this idea before, where you take the product of a number by itself and try to solve an equation. And this is another way of expressing that same procedure. Okay? Because what does this represent? A number multiplied by itself that has to be equal to 3. Okay, that's what we have here, a number multiplied by itself. And what's it equal to? 3. So that number x must be 3 to the 1/2. But we already have a way of interpreting the solution to this equation. Okay? When we solve this equation here, and we're going to solve just for positive values, we know that we solve it by taking a square root. Okay? So this number that multiplies itself to give you 3 must also be equal to root 3. So that means 3 to the 1/2 must be equal to the square root of 3. Okay? Let's look at another example to see if the same thing's occurring. Okay, let me take 5 to the 1/2 times 5 to the 1/2. So a number times itself. Okay, and when I add up the exponents, I just get 5 to the 1. So a number times itself is equal to 5. That's the same thing as solving this equation. A number times itself is equal to 5. And of course, we know that solution as square root of 5. So that means that this number here, okay, must be equal to 5 exponent to the 1/2. Okay? So now we've found a meaning for the exponent 1/2. It's equivalent to square root. Okay? So again, if we think about our basic functions, when we were looking at y equals square root of x, again, we have a function that now can be expressed as an exponent, just like the reciprocal function was. So there was more in common with those functions than we might have thought at the time. Okay? Let's see what happens when we're trying to figure out what 1/3 means. Okay? In order to create the same kind of scenario, it's not enough to just multiply 4 to the 1/3 times 4 to the 1/3. I add those up, that just gives me 2/3. So I need to multiply it a third time. Okay? So when I multiply these three together, same base, so I can add the exponents. So 1/3 plus 1/3 plus 1/3 is just equal to 1. So this must be equal to 4. So I have a number multiplied by itself 3 times, equaling 4. That's the same as solving this equation. X cubed is equal to 4. Now, hopefully, you might remember where you would have seen an equation like that in grade 9. Say you were given the volume of a cube as, I don't know, say 27. Okay? Well, how do you find the volume of the cube? You take the side length and you multiply it by itself 3 times. So x cubed is equal to 27, and how does one solve that? By what's called the cube root. Okay, in this case here, it's a perfect cube, because that's just equal to 3. You would have also seen it when you were solving problems involving volumes of spheres, because the volume of a sphere is given by 4/3 pi r cubed. So if you were solving for the radius, you would have had to use the cube root. So when we solve this equation of a number multiplied by itself 3 times equaling 4, the solution to that is just the cube root of 4. Okay? Now you can take this further. What about 6 to the 1 over 5? Okay? If you continue this argument in a very similar fashion, you would find that this must be equal to the 5th root of 6. Now let's think, what would the 5th root of 6 be? Well, it's that number such that if you multiply it by itself 5 times, would be equal to 6. Okay? A nice 5th root would be 32. 5th root of 32 is 2, because 2 times itself 5 times is just equal to 32. So it looks as though we found a meaning for any fraction with 1 in the numerator. So the power x to the 1 over n is equivalent to what we call the nth root of x. Okay? So if it's the square root, it would be the number you multiply by itself twice to get x. If it's the 10th root, it's the number you multiply by itself 10 times to get x. Okay? So now what we're going to do is we're going to put everything together in a note so that we've got something to refer to. Okay, so we're not going to make this into a whole new unit because, again, the goal is to get to this last type of function. So I'll call this unit 5a. So first we'll do some work on figuring out what all these exponents mean, and then we're going to be looking at the exponential functions. Now notice it's not just the exponential function, because if I change the base, it makes sense that I would get a different type of function. Hopefully they'll have stuff in common, but they will be different functions. Okay, so let's start with a recall. Okay, and that's our exponent laws. Okay, so number 1, we have the product law, so x to the m times x to the n. So I'm not going to write out that the bases have to be the same. It's implied in the way I've written the expression. So that's just equal to x to the m plus n. Okay, then we have the quotient law, x to the m over x to the n. That's x to the m minus n. And then we've got the power law, which is x to the m to the exponent of n, and that's x to the m times n. Okay, so this is what we knew from before. Okay, so now we'll make a list of all our new discoveries. Okay, so we'll start with negative exponents. So x to the negative n we saw was just equal to 1 over x to the n. Okay, and in particular, there's that special one that we've already studied before. Okay, so in particular, x to the negative 1 is 1 over x. Okay, but here I want to make sure we think about any restrictions that we have. Okay, and since now x to the n is going to be in the denominator, we see that x can't be equal to 0, similar to what we had with the reciprocal function. So here we'll specify if x is not equal to 0. Okay. Next we'll go to x to the 0, and we saw that that's equal to 1. So the question is, are there any restrictions here? So if you recall how we came up with this rule, we saw that we had to divide two powers. Okay, so again, if that base is equal to 0, this won't work. Now I'm not going to talk too much about this idea of 0 to the exponent of 0, but just to let you know that that's something that's going to become very important when you study calculus later on. Okay, so here we'll say again, if x is not equal to 0. Okay, now number 3, we've got our rational exponents, or at least some of them. So in the next class's lesson, we're going to see how we deal with rational exponents beyond just 1 over n. But if you have x to the 1 over n, that's the same thing as what we call the nth root of x. Okay, so this is the nth root. Now, by convention, if we're dealing with a square root, we don't bother putting the little 2. Okay, since that's the most common one, if you don't see any number there, you assume that it's a square root. Otherwise, you have to specify which root you're talking about. Now, another important thing to think about are the conditions on x. For example, we know that if it's a square root, x can't be negative. Now, think about a fourth root, where you have to multiply a number 4 times to get x. That'll always be positive. So again, for a fourth root, a sixth root, in fact, any even root, x can't be a negative number. Okay. Whereas for an odd root, say cube root, when you multiply a negative number 3 times, you will get a negative number. So you can take cube roots of negative numbers. Okay, so here we have to give a double condition. So here, if n is even, then x has to be greater than or equal to 0. And if n is odd, then x can be any real number. Okay? So, that's it for now. Next class, we're going to go a little further with rational exponents. Okay, but for now, please make sure that you get the homework done so that you review all these exponent laws. Okay, thanks.